and have Donna, Rebecca. I want to ask you to, in this, during 15 minutes, to consider the group without associative law, which is gyrogroup. Okay. My talk is about gyrogroups and the structure of G-graph of these gyrogroups, this structure. First of all, I started with some definitions and some main result about G-gyrograph, which is the G-graph of the gyrogroup of a special class of gyrogroup shown by Gn, and that has some references. Gyrogroup was discovered by Abraham Ungar in his study of the parameterization of the Lorentz transformation. A gyrogroup can be considered as a group without associative law that is replaced by gyro-associative law and left loop properties. The first example of gyrogroup is given by him in 1988, that he applied Einstein's velocity addition as a gyrogroup to a unit sphere. It is a group either we see with O plus E that is defined here for X and Y belongs to R3 over C, and the form of X, the size of X is at most C, and you can see the product of these vectors that is defined by this formula. Here there is a definition of a gyrogroup. An empty set G together with the binary operation O plus that is satisfied in these four axioms is called gyrogroup. The first one, identity element. The second one, the inverse of each element. The third one is a gyro-associative law, and fourth one, left loop property. Here there is a function of gamma that carries every pair of AB to gyro of AB of C is equal to this. And we call a gyrogroup G a gyrocommutative if and only for every A and B inside G. The AO plus B equals the gyro of them and of BO plus A. We say H, which is a non-empty subset of G, is subgyrogroup if it is a gyrogroup under the operation inherited from the gyrogroup G, and for every A and B belongs to H, the gyro of A and B of inside H is equal to H. And we call it L subgyrogroup if for every A belongs to G and H belongs to H, the gyro of H is equal to H. By this condition, we can consider the right coset of H, and we can see that this is the partition of G, and the order of H divides the order of G. A subset S of a gyrogroup G is said to be symmetric if the inverse of each element of S is inside S. Consider this set that is a left-generating set of gyrogroup G, and if every element of G can be written by production of these elements, but this set, then we say that G is left-generated by S. This is the subset of generating set of S. Here there is a definition of G-graph. As you know, the graphs are good tools, suitable tools to study about the graph. So I studied about G-graph of the group, and here and in the future I want to consider the G-graph of gyrogroup. It is introduced by Alan Barreto in 2005 from Caen University, and the set of vertices of this structure are such cycles. You see that is supply of right cosets of each Sx, and this cycles is x to the S or to the OS minus 1x, These are the vertices, and two vertices are adjacent even only if the intersection of their right cosets has at least one element in common. Here there is an example of gyro group G8 with the addition table, gyro addition table and gyro automorphism table that equals 1, 6, and 2, 5. Here there is a structure of G graph of the gyro group that I called it G gyrograph. You see where S equals 1, 2, the structure of G gyrograph that is shown by phi. G8 is bipartite because the size of S is 2. The first line are the vertices in part of V1, and the second line are the vertices in V2, and this graph is regular. The vertices are such pairs that each pair has two elements in common with the vertices in another level. And but this is disconnected and contains two C4. Note that here G8 is not left generated by S, but is generated by S. Here, another example where S equals 1, 3. The structure of a G gyrograph is again bipartite. And here, G8, gyro group G8, is left generated by S. And this graph is connected. You know, another example. Here, S it has 3 elements, 1, 2, 3. And G8 is left generated again by S. And you can see that this graph is again connected. 4 regular and all vertices are such pairs, and since S has 3 elements, it has 3 parts, you know. I believe that these are related, where gyro group G8 is left generated by S, and then the G gyrograph would be connected. There are some papers, some research about Cayley graphs of gyro groups, for example, by Busaban. The Cayley graph of G8 is considered with some subsets S, and he believed that for a gyro group G with a non-empty symmetric subset S, the Cayley of G and S is connected even only if G is left generated by S. But I want to consider the two gyro group is a special class of gyro group which is shown by Gn for an integer n greater or equal than 3. This is constructed by Ashrafi, Ungar, and 2 other authors, whose every proper subgyro group of this structure is either a cyclic or a dihedral group, and you know, consider these two subsets. Our structured gyro group Gn is the union of these subsets. I will show 2 to the n minus 1 by m. Yeah. Depends on I and j belongs to Pn or Hn. The pair I-J belongs to the direct product of them, and I-O plus J would be equal to one of these 4 numbers, that T, S, K, R belongs to Pn. Here there is a function of gyromorphism that carries every element x in Gn to x, or R plus m depends on x belongs to Pn or Hn, and the gyromorphism with this function. These are the subgyro groups of this structure. Itself, the subgroup of Pn. The third one, the subgroups that are isomorphic to Z2, that J belongs to Hn, and this structure. And you can see that the subgyro group of generated by 1, 2, up to 2 to the n minus 2 are cyclic group, and generated by 2m and 2m plus 1 are isomorphic to the dihedral of the m. And these are the elements of Hn that their cyclic subgyral groups are also L subgyral groups of Gn that are isomorphic to Z2. Here there is an example where n it would be 3. This is the gyro addition and gyro automorphism table of G3. Here the structure of G gyrograph of G3 with P3, one of that do both subsets. Since the cardinality of P3 equals 4, then this graph would have 4 parts, and one is V1, V2, V3, and V0. You can see that, for example, by the definition of G graph that I told you, the vertices of V1 would be 2 vertices of the cycles of length 4. And for V2, we have these pairs, 4 pairs. V3 also has 2 vertices of cycles of length 4. And this is the V0. We can see that this structure is 4-partite and connected, but not regular. And another example, when G3, we have G3 with H3. The structure of G gyrograph would be 4-partite because of the size of H3 equals 4. It has 4 parts that every element inside Hn makes a cyclic subgyral group J isomorphic to Z2. Then also they are L subgyral group. Then we can see that each part is of size the index of Vj inside G3, which is equal to 4. And you can see that all vertices are the pairs. Each pair has exactly 2 elements in common with the vertices in other level. And it would be 2 times m minus 1, which m equals 4. Regular, that would be here is 6. And it would be better to say conjecture at the theorem. I believe that the structure of G gyrograph of Gn with Hn is connected and Hamiltonian. You know, it has the size of Hn, which is equal to m, 2 to the n minus 1, I called m. And parts, there are m parts. Each part has each part has m vertices of form of pairs. That each pair has 2 elements in common with the vertices in other level. So it would be 2 times m minus 1 regular. And by using some theorem inside the graph theory, that the degree of each vertex is greater than the number of vertices, that would be Hamiltonian. It means there is a path that carries all the vertices once, and it would be connected. I think the Gn can be left generated by the elements of this subset Hn. That's it, and I want to thank my supervisor, Professor Ashrafi, and these are the references I used about G-graph, about gyrogroup. I'm interested in graph theory because, as Rebecca said, she likes the finite groups that we look at inside the group. I like graphs to see the properties of groups better and better. Thank you so much.